think we can start. My name is Constantinos Taliotis. I'm a postdoctoral fellow here at the Cyprus Institute. Today I will present a topic that was prepared actually by a colleague, Nestor Philaktos, but since he's away on business, I'll be substituting him. And today we will be talking on the topic of the basics of CSP Economics. So far you've been looking into the technical aspects of technologies, but today we will focus mostly on the economics. So it's not only important to look at the technical feasibility of technologies, but also the financial feasibility of technologies. So just a brief overview on the topics that I will be discussing. We will look first into some basic investment tools, then into some essential concepts regarding CSP technologies. We'll talk about the different types of costs that characterize these technologies. I'll give you some examples, and then we'll close the session by looking into the trends and future cost estimates of CSP technologies. And by the way, feel free to interrupt me at any point in time in case you have any questions or something is not clear. To start with, we should be aware of the notion that in economic theory, there's the idea that money today is worth more than money tomorrow. So a euro in hand today is worth more than a euro in hand tomorrow. And the concept behind this is that money has interest earning potential. So you can take that euro, invest it in a bank or in a business, and you get more money out of it into the future. So this is a concept that will govern the whole presentation, basically. Money today is worth more than money into the future. So investment in several projects entails initial capital investment costs, but also a series of annual cash flows into the future, either negative or positive. And to assess the feasibility of a project, the financial feasibility of the project, we need to compare these cash flows, present and future, with a common basis. So we need to discount the money that will enter the project or leave the project into the future into a common basis, which is the present value, so the present value of money. The reverse operation, so basically looking into how much money today will be worth into the future, is called capitalization. Whereas estimating the present value of future cash flows is called discounting. So what's the present value? The present value is basically, it can be calculated by looking at the future value of money and dividing it by 1 plus the discount rate to the power of the years that separate the present and the future. And the higher the discount rate, the lower of the present value of future cash flows. So if we look at an example here, we have 1,000, maybe I shouldn't approach that. So we have 1,000 euros. If we have a discount rate of 10%, in 7 years it will be worth 513 euros. But if we increase the discount rate to 15%, the present value of this 1,000 euros drops to 376 euros. So what's the discount rate? The discount rate is basically the interest rate used in discounted cash flow to determine the present value of future cash flows. And it basically represents it takes into account not only the time value of money, but also the risk or uncertainty in receiving these future cash flows that we estimate will receive into the future. So the higher the discount rate assumed while assessing a project, basically the higher the discount rate. Higher uncertainty equals higher discount. And there's two types of discount rates. There's the nominal discount rate, which takes into account inflation, and the real discount rate, which excludes inflation rate. So the inflation rate, for those who are not aware, is basically the rate at which a certain basket of goods, a certain set of goods, increases over time. And basically the way this is usually calculated is taking a set of basic goods, such as bread or milk, electricity, and so on, and comparing the price of the past and the future. Maybe this set of goods would cost 100 euros today, but maybe next year, with a 2% inflation rate, it will cost 102 euros. Clear so far? Moving on from the present value, we have the net present value. So basically the net present value is the difference between the present value of cash inflows and cash outflows. So costs and income for a specific investment project. So in essence, the net present value estimates the amount of wealth that can be generated by a certain project for the investors over the entire period of the project's lifetime. And for, if we're assessing specific individual projects on their own, so let's say we want to build a hydro dam in a certain area of the country, and we want to see if it's financially feasible or financially beneficial. If the net present value is above zero, we basically accept the project. But let's say instead of looking into building a hydro dam, we want to compare different options. We can build either a hydro dam or a CSP project, or a CSP plant, or a nuclear reactor, or whatever generation option we might think it's feasible in the area. So the way of comparing which project is more financially beneficial, it will be through looking at the net present value of each of these projects. And the higher net present value associated with a specific project would be the optimum for this specific case. How do we compute this net present value? Basically, we take into account the cash flows for each year, and we discount it backwards, as we showed earlier for one specific value. And then we sum up all these discounted cash outflows or inflows to get a specific net present value. So if we look at an example, a project, for instance, might require an initial investment of $100,000, and over the next 5 years, it will generate cash flows of 70,000, 30,000, 30,000, 25,000, and 50,000. And if we assume a discount rate of 17%, we can see whether it's a worthy investment or not. And by discounting all the cash inflows or outflows, we get a net present value of $18,000. And since this value is positive, then we can see that the project is beneficial. Clear so far?
But isn't 17 a very high discount rate?
Yes, it could be a very high discount rate. It depends on the risk or the uncertainty that we assume these cash inflows are associated with. I'll give some examples on discount rates later on and see how different rates affect the price of a project, the electricity cost, for instance. In the case of developed countries, for instance, discount rates that are assumed in assessing projects are around 5%. But in developing countries where the risk and uncertainty is much higher, the discount rate can range between 10 to 15%. So 17% in this particular example might be too high. Yes.
sorry, that's the real or the nominal?
Sorry?
The real or the nominal discounting?
In this case, it doesn't really matter. It's an example. You can assume it's the nominal. So, including inflation. So this net present value criterion has some benefits, but it has some disadvantages as well. It takes into account the time value of money. It takes into account the entire cash inflows and the outflows for the entire project duration. And it represents the value added to the investors. And it's quite relatively simple to calculate. But it's very sensitive to the discount rate. So the actual value that we get at the end is it's highly dependent on the discount rate that is assumed for the project. While some people might find it a bit difficult to understand the benefits of the project on a mere monetary value, on a single monetary value, instead of a fraction or a percentage return on their investments. And this is where the internal rate of return comes in. So the internal rate of return is a rate of return that makes the net present value of all cash flows, either negative or positive, from a particular investment equal to 0. It can also be defined as a discount rate at which the present value of future cash flows is equal to the initial investment. So basically, the rate of return at which our investment breaks even. And if you see the equation that characterizes this criterion, internal rate of return, is very similar to the one used for net present value. So if we go back, you can see that it's the sum of the discounted cash flows. But if we replace discount rate with internal rate of return and equal the equation to 0, we can calculate the internal rate of return. So these calculations are basically used to evaluate the financial desirability or attractiveness of investment projects. And if we're comparing a number of different alternatives, we usually select the project which has the highest internal rate of return, assuming the investment cost is the same for each of these projects. And another decision criterion would be if a project's internal rate of return exceeds the discount rate assumed for the project, it's basically beneficial. So if the discount rate is 7%, while the internal rate of return is 10%, then we can assume the project will add value to the investors. If we look at the same example as earlier, assuming a discount rate of 17% and the same initial investment and the same cash inflows into the project, we can calculate the internal rate of return for this project. It's basically where this line crosses 0. And we can see that the internal rate of return, where the net present value is 0, is at 27.68%. So it's a quite high internal rate of return. And it exceeds the discount rate. So in this particular example, the project is beneficial. Any questions so far? No? So even though a project might have a single net present value, it can have multiple internal rates of return. And this is the case in examples where, or in cases where cash flows might be positive and negative throughout the duration of the project. So for instance, if a project has an initial investment of $235,000, a cash inflow of $540,000 in year one, but a cash outflow, so again a cost in year two of $310,000, we can see what the internal rate of return is in this case. And by doing again the same calculations, we see that the internal rate of return, so the net present value is zero between internal rates of return values of 10 and 20%, while the net present value is only positive in between these two, while in other areas this is negative. So basically what this tells us is that if the discount rate assumed for this project is in between these two values, 10 and 20%, then the project is beneficial. If not, then we would have to reject this particular investment. In terms of advantages and disadvantages of this indicator, this internal rate of return, similar to the net present value, it takes into account the time value of money. So again, we discount money backwards to get the net present value. It considers cash flows for the entire project duration. And it's easier to understand for people who want a percentage value of their investments, their return on investments. As opposed to net present value, which just gives a final monetary value for at the end of the project. Its disadvantages is that it's relatively more difficult to calculate as compared to the net present value. While figuring out or understanding the concept of multiple internal rates of return is a bit complex and not many financial managers can understand that. Moving on into a much simpler concept, the simple payback period. So basically this characterizes the amount of time needed to break even for your investment. So in this particular project, we have an initial investment of 60 million euros, cash inflows of 20 million euros annually, and maintenance cost of 1.5 million euros. So if we divide the initial investment by the net positive inflows, so we have an income of 20 and a cost of 1.5 each year, we see that we break even on our investment after 3 years and 3 months. So it's a very, very simple calculation. And the shorter the payback period, basically the more desirable this project is. So it generates income much, much faster. The same concept, but basically discounting all future cash flows, similar to what we did for the net present value, gives us the discounted payback period. So if we go back, if we would discount for each particular year, in year one, we discount this for 1 year, in the second year for 2 years, and so on, the payback period would basically increase because the value of future cash flows would decrease. And again, the shorter the discounted payback period, the more profit this project generates. And in either of the cases, either in the simple or discounted payback period aspects, a project would be accepted if the payback period is shorter than a pre-specified period of time. So let's say if the investor wants to break even on his investment in the next decade, and the payback period is before that, then it's definitely a profitable investment. The strengths and weaknesses of this payback periods aspects, so basically they measure risk and liquidity. and they're useful for evaluating small projects. So it's a very simple calculation, or very simple comparison that we do. But the disadvantages is that they ignore the time value of money in the case of simple payback period, and it ignores cash flows after the payback period. So it doesn't take into account what happens after you break even for the project. Because maybe after that you have to conduct certain maintenance. That's
Replacement.
yes, replacement of equipment that would bring costs into the project and might affect the attractiveness of the investment. So out of these investment indicators, which one is most commonly used? They all have their advantages and disadvantages. But investors typically look into several of these criteria. And the most common are the net present value. So how much value is added into the project at the end of its lifetime. And the internal rate of return. So basically how fast an investor gets their money back or breaks even. And these payback period aspects are less frequently used. Any questions so far? No? A more common indicator that you may be familiar with is the levelized cost of electricity. And this levelized cost of electricity is basically a measure of assessing the attractiveness or competitiveness of different generation technologies. It basically represents the per kilowatt hour cost of building and operating a power plant over its entire lifetime. So, for instance, for a coal power plant, we would have, let's say, a levelized cost of electricity at somewhere between 5 and 8 cents, dollar cents per kilowatt hour, depending on the cost of fuel, of course. And we have these metrics for all different types of technologies, and I'll show some examples later on. And this levelized cost of electricity is the most usual metric when trying to compare the attractiveness of electricity generation plants and sometimes other energy technologies. What does this include? It basically takes into account installation costs, so how much does it cost to build the plant, financing costs, so getting a loan and financing the project, taxes on the equipment or on operating the plant or on the salary costs and so on, operation and maintenance costs. Then we have salvage values, so at the end of the lifetime of the project, maybe we can sell part of the equipment as spare parts, for instance, and get some extra revenue. We might have some incentives, so grants by government, let's say, that reduce the installation costs of a particular project. And we take into account the quantity of electricity that is generated by the particular plant. So how much electricity is generated not only annually but over the entire duration of the plant. And the gradation of the output. So perhaps the efficiency of the technology drops over time, either through wear and tear or yeah. And a couple of other aspects that might be taken into account are environmental costs. So for instance, in the case of fossil fuel power plants, perhaps there's a carbon tax. So for each ton of CO2 that you emit, perhaps there's an extra added cost that you need to take into account. And there might be transmission costs associated with the investment as well. So if the plant is going to be situated in a very remote location, the transmission costs, so connecting this power plant to the main transmission and distribution network might be quite high. So how is this levelized cost of electricity calculated? It's basically calculated by summing up all the project costs and dividing by the amount of electricity generated by the plant. So it's a relatively simple calculation. And this can be done either annually or throughout the project's duration. And if we rewrite this equation, so the cost of the total cost of the technology can be estimated by multiplying the levelized cost of electricity generation times the amount of electricity. So this is expressed in dollars per kilowatt hour times kilowatt hours generated by electricity. We get dollars here. If we look at the total life cycle cost of the project, we can estimate this by summing all the costs and discount it back to a present value. So similar to what we did for the net present value earlier, we can do the same to estimate the total life cycle cost of a particular investment. And the discount rate again is used to calculate this net present value. And similar to what we did earlier, where we rearranged the equation here to express costs in terms of LCOE times amount of electricity, we can rewrite this equation in terms of generated electricity. So by discounting the amount of generated electricity times the LCOE, we get again the total life cycle cost. And if you can see here, the number of years starts from the first year, and that's because the electricity being generated only starts in the first year of operation. In year 0 here, we only have the investment costs. We have no electricity being generated. And by combining these two equations and rearranging them, we again get the final formula for calculating this LCOE, in which we basically divide the total discounted costs of the project over the entire duration of the project by the discounted electricity generations of the project. Clear? Yes. The conceptual meaning of LCOE, it basically is a proxy for the average price the generating asset must receive in a market in order to break even over its entire lifetime. So basically, if you sell the entire electricity generated by the plant at this LCOE cost, then the net present value of the technology will be 0 at the end of its lifetime. So in order to generate profit for a particular investor, the electricity that they need to sell must be actually above the LCOE price that you calculate. For technologies that have no fuel costs, so renewable energy technologies, what drives what affects the LCOE level is basically the capital expenditure of the project. And this capital expenditure can be affected further either by incentives such as tax breaks or grants or so on. But for technologies that have significant variable costs, like fuel costs in the case of fossil fuel power plants, these are the main driver for increasing or decreasing the LCOE level of a particular generation option. The LCOE is a single dimensional number that gives a lot of information but doesn't manage to capture all factors. So the LCOE doesn't take into consideration the true value of systems with storage. It doesn't take into account the time availability or the time variability of each option. So you might have an area with a very high solar resource that would bring the LCOE of CSP technologies down, let's say. But if that, the LCOE of CSP technology is down, yes. But if that technology has no storage, it can only produce basically when there is sun. So even though the LCOE of the technology might be, let's say, 10 cents as compared to 12 cents for a fossil-fired diesel generator, you can't rely on just the technology just because it has a lower LCOE. The time variability and the availability of storage also needs to be taken into account. Similar concept, the dispatchability of the plant. So how easy is it to respond to changes in demand? So can we ramp up the generation of a plant or not? This is much trickier in the case of renewable energy technologies in the absence of storage. Then there's other services that can be provided by generation technologies that have no monetary value, such as frequency response and frequency support and voltage support. And there's frequently poor treatment of externalities. So a lot of calculations don't actually take into account the cost of greenhouse gas emissions. Or they might not take into account the cost of pollution of the different generation technologies, which is also a cost that should be taken into account to look at the entire impact of a technology. Moving on, you've already looked at the different types of CSP technologies, I believe, right? And these different types of CSP technologies have different characteristics that also affect not only their performance, but also the economics of these CSP technologies. We'll look at some examples now. So some fundamental aspects, basically to start with, the capacity factor. The capacity factor is basically the ratio of actual generation from a particular technology as compared to the theoretical output of that technology. So for instance, 1 megawatt of particular generation technology could in theory generate 8,760 megawatt hours in 1 year. So the amount of hours in a year multiplied by the nameplate capacity. But if the capacity factor is lower, if it only generates at 50% of its level, so 4,380 megawatt hours, then the capacity factor is 50%. For baseload generation technologies such as coal and nuclear, where they basically work almost constantly throughout the duration of the year, the capacity factor is typically around 90%. In the case of hydro plants, a general number is around 50%, but this is highly variable. So there's hydro plants that have dams that might have a much higher capacity factor. There's hydro plants that have no dams, but they have a constant flow of water that doesn't decrease over time, over the year. There is no seasonal variation that might be higher than 50. Or the seasonal variation of rainfall, for instance. If there's a dry period in the country, will decrease the capacity factor, it might be lower. So it's very, very location specific. In the case of intermittent renewables, such as PV and wind, the capacity factor can range between 15% or 50%, again depending on the location and technology. Whereas in the case of CSP without storage, this is typically around 20 to 30%. Everyone understand the concept behind capacity factor? Yes. In the case of solar multiple, the solar multiple basically determines the receiver's nominal thermal power. And it's basically the ratio of the thermal power of the receiver to the cycle thermal power. In other words, it's the size of the solar field needed to deliver the thermal energy required to drive the power cycle of a CSP plant at its nameplate capacity. And for a system without storage, the solar multiple is usually close to or equal to 1 in order to drive the power cycle at its peak. But in systems with storage, we can choose higher solar multiples as because we can store the thermal energy and then drive the power cycle for a longer amount of time, and not only when there is sun available. And the size of this solar multiple is basically determined through techno-economic optimization. And this also determines the size of storage, of course. The different types of costs that characterize CSP and solar thermal plants. Basically, we have capital expenditure, so upfront costs, the cost that we have in order to put the power plant in place. And this can be further broken down into equipment costs. In the case of CSP, it's, for instance, solar receiver, the solar field, the storage system, the power block, and potentially other components, such as a desalination add-on, in case it's a cogeneration plant for electricity and desalinated water generation, or cooling equipment. Then we have land and site preparation costs, so we need to prepare the site before we bring in the equipment and install it. And we have engineering, procurement, and contracting costs that are often characterized as indirect capital expenditure costs. Then we have operation expenditure, which relate to operation and maintenance costs. And this can be broken down into fixed costs and variable costs. The fixed cost could be, for instance, the salary cost. So it doesn't matter how much the power plant will generate, you will always have this salary cost. If you have a specific set of people working there, you will have to pay them accordingly. But in the case of variable costs, this is affected by how much the power plant generates. So with the higher rate of use, you have a higher rate of need, higher necessity for maintenance of the equipment. And then we have financing and taxation costs. So financing is basically the costs incurred when borrowing the cost of capital, basically, needed to make your investment. And taxation costs is highly dependent on what the particular location is, or the particular country and technology is. By doing a small example in the system advisor model, Nestor actually built for 4 different technologies: parabolic troughs, solar tower near Fresno, and parabolic dish. 100 megawatt electric nameplate capacity plant for each of these technologies. And weather and solar resource data were used for Larnaca, a city in the southeast, so where you arrive by airport, I guess. And he made an estimation of the upfront cost in terms of $1 million for the different components. So in the case of site improvements, comparable costs could be observed. Then in the case of solar field, again this varies a bit according to the technology. Then for the tower, receiver, and heat transfer fluid system, this varies much more. We can see that for the tower option, the cost is much higher. Then for the storage component, we have a very high cost in the case of parabolic troughs, and this is basically because of the temperature difference. So for in the case of tower systems, for instance, the temperature of the heat transfer fluid can reach much higher levels. So when we're trying to store the thermal energy, the size of the storage can be much smaller than in the case of parabolic troughs, where the temperature is much lower. And since the temperature is much lower, we need a much bigger storage system, size of storage, in order to store the same amount of thermal energy. In the case of the power cycle, we can see how this varies for each of the technologies, and the balance of plant. So this relates to components such as transformers or inverters that might be needed for the power plant. If we look at this breakdown, which technology would you think is more beneficial? So we're looking at the upfront cost for a 100 megawatt electric plant with the dish.
But no storage.
But what is in our storage and DLP dish?
Yeah, I'm not actually sure exactly what happened here, but I think there is no storage.
No, in some there is no storage for dish.
Yeah, in this particular case there is no storage. But just by looking at this, you would think that the dish is basically the most beneficial option, right? But this doesn't really tell us how much each of the technologies generate over time. If we look at the capacity factor, we can see that the dish has a much lower output, generates much lower electricity than any of the other plants, and it is related to the absence of storage. And in the case of the dish, the capacity factor is about 15%. Then for Fresnel, it's about 27% or 25%. 27% for troughs, and about 35% for the tower. So we would have to see not only what the upfront cost is, but also the operation and maintenance costs and how much the plant generates. So if we do an LCOE calculation, a levelized cost with electricity calculation, as I showed earlier, it would be easier to make a comparison and an assessment. In terms of operation and maintenance costs of CSP plants, these are highly dependent on the capacity and not so much on the energy generation. So, as I mentioned earlier, renewable energy technologies don't have very high variable costs. They do have quite high fixed costs, which are related to staff costs, insurance, and maintenance. In the case of CSP technologies, the operation the maintenance is mostly related to cleaning, as well as the replacement of mirrors in case they break. While we might have quite high costs in case these plants are deployed in arid environments, and we need water for cleaning of the mirrors. So in case there is an environment with a very high and very low access to water, it might be challenging to clean the mirrors using them. So it adds an extra cost to the system. But innovations such as efficient plant monitoring, low soiling surfaces, so avoiding dust or particles from settling on the mirrors, and better understanding of degradation can reduce these operation and maintenance costs. The actual costs that are incurred by plant operators are not really well known because they're not published. They're confidential information. But the estimations show that for parabolic troughs, these are around $70 per kilowatt per year, while for towers, these are around $65 per kilowatt per year. And of course, in case of more developed countries with higher staff costs, the operation and maintenance costs would be proportionally high. And reductions in these particular estimations can be realized through automation of processes such as washing, better plant design, or lamination of mirrors to avoid dust or soil from settling on them. Here we have an example of a 100 megawatt parabolic trough plant, where you can see that the variable operation and maintenance cost is only 8%, whereas the fixed operation and maintenance cost is 92% of the total operation and maintenance cost of the plant. And this is broken down mainly into maintenance of the solar field and storage as a first factor, then insurance and staff costs, and to a lesser degree maintenance of the power block. Moving on into another cost category, the category of financing costs. This can be quite significant and should not be ignored. The weighted average cost of capital basically describes the creditworthiness of an investor. It takes into account the assets owned by a company, let's say, as compared to the long-term debt of the company. And the weighted average cost of capital basically represents the minimum return that the company must earn on an existing asset base to satisfy its creditors, owners, or other providers of capital, so that they don't invest elsewhere. And the way this is calculated is basically by multiplying the share of equity, so basically assets, with the cost of equity, and adding that to the share of debt as compared to the total equity and debt, and taking into account the corporate tax. And the cost of equity is essentially the amount that the company must spend in order to maintain a share price that satisfies the investors, whereas the cost of debt is the rate that the company is paying for its debts, usually to a creditor such as a bank. So, very roughly, the weighted average cost of capital is basically the average of the costs of debt and equity finance. And we'll see how this affects the price of electricity from a plant, for instance, in an example that I'll show later. Ways to support the CSP system, so, and not only a CSP system, but other renewable energy technologies. A common method that was used in the past in Europe was the feed-in tariff. So basically, getting a fixed price for every kilowatt hour that is delivered by a system. This was a very popular system in the past, but now it's used less and less as due to the decline of costs of technologies. Many governments have also been losing money because they didn't anticipate how many investments will happen in these technologies. Similar concept is that of the power purchase agreement, where a bilateral agreement in which a fixed price of selling each kilowatt hour generated by the system is signed between a producer and the utility. Other measures that could include grants or subsidies to that affect the investment cost, the capital cost. So getting a fixed amount of funds for each kilowatt of plant for a CSP system that you install. Or there could be slightly more complex schemes, such as net metering or tariffs depending on time of delivery. In Cyprus, we have, in the case of rooftop photovoltaics, we have a net metering scheme, for instance, in which households are allowed to install up to 5 kilowatts of photovoltaic, and then they pay only the amount of electricity consumed that exceeds the amount of electricity that is produced by the photovoltaic system within a specific year, calendar year.
So they pay the electricity once a year after everything's calculated?
Yes, yes. Or they might pay every bi-monthly, every 2 months, but then at the end of the year there is a matching system. If we look at some of these concepts in the context of a particular example, so a test case of a 4 megawatt electric linear Fresnel system was built in the SAM, the System Advisor model of Endor. The linear Fresnel system focuses light on a linear receiver, as you know here. It has a lower optical efficiency as light can bounce off outside the receiver area. But it's less sensitive to wind because of its shape. It's it has less weight. It uses lower amount of land. And the components are easier to manufacture, especially because they're flat and not curved as in the case of parabolic traps. And this system can use various heat transfer fluids such as water, oil, or molten salt. In this particular example, direct steam generation was assumed, and weather data for Cyprus was used. Looking at the system costs of the particular system, we get an overall cost of about 12.8 million euros. If we divide by the capacity, the total capacity, this comes to about 3.2 euros per kilowatt. The debt fraction assumed was 7% for 15 years. Basically, the debt fraction is the ratio that measures the extent of debt as compared to total assets of a company. So it's basically the proportion of a company's assets that are financed by debt. Then we assume an income tax rate of 12.5% and a depreciation schedule of 10% linear. So just a small parenthesis on what depreciation is. It basically represents the decrease in the value of the project, mainly due to wear and tear. It's not actually a real cost, but it's an accounting principle to reflect the fact that the equipment bought or built loses value over time. Many countries have specific schedules to be used. In Cyprus, legislation says that a linear 10% must be used, but other countries can use non-linear schedules, such as in the US. And basically a linear schedule of 10% would indicate that the value of the equipment after 10 years is 0.
You don't even assume some salvage value at the end?
It does a bit. I'll show it in the figure later. Looking at the results from the plant output, we can see the total power incident on the solar field, the light green bars, the thermal energy delivered to the block, and the gross cycle power output in red. And this is basically a monthly profile of electricity generation, let's say. And by averaging that electricity generation, we can see that the plant's capacity factor is at 22.06%. You can see here that the cost of investing in the project and the cash flows in the subsequent years. 25 years was the assumed project duration. And you can see here at the end of the financing period that there's a very small salvage value. So the difference between year 24 and 25. So there's a small increase in the amount of money received by the project. And the bars here are basically lower because of the cash used to pay off the plant. And by summarizing the results of the project, we see that in order to achieve a 10% internal rate of return, which is usually the rate aimed for by investors, the power purchase agreement, so the price at which electricity should be sold by this plant, should be about 25 euro cents per kilowatt hour. And this would achieve a net present value at the end of the project of $2.2 billion. But what do you think of this price of electricity? Do you think it's realistic?
It's a bit high.
High.
Yeah, it's
Quite high. In Cyprus right now, I think the avoidance cost of, so what the utility pays renewable energy generators for providing electricity is between 5 to 10 euro cents. Not sure exactly what the rate is, but it's in that region. If we allow the power purchase agreement price to vary between 0.12 and 0.3 euros per kilowatt hour, we get different net present values and different internal rates of return, so for each of these. And we can see that the net present value becomes positive only after reaching the 0.22 euro cents per kilowatt hour, which is quite high. And similar to before, as we seen earlier, the internal rate of return is only at about 25 euro cents per kilowatt hour. So in this particular project, the goal would be to decrease the cost of electricity generated. The possibilities to do this could be, for instance, by addressing the operational maintenance costs, or trying to reduce the capital cost somehow, or achieving better financing terms, so a lower cost of capital. If we look at the trends for technologies globally, we can see that CSP has actually improved quite a bit in between 2010 and 2017. So we can see, if we start from the left-handmost corner, we have biomass, geothermal, hydro, solar photovoltaic, CSP, offshore wind, and onshore wind. We can see that the most rapid price improvement was achieved by solar photovoltaic. So in between 2010 and 2017, it achieved almost 70% decrease
Because of the
in
Chinese.
LCOE. Sorry?
Because of the Chinese.
Yes. Yes. So lower cost of capital, like lower capital cost of the equipment. And all these, the lines basically are weighted averages for each of the technologies. And all the dots show different installations according to the size. So the bigger the dot, the bigger the size in megawatts for each of these technologies. And you can see that, for instance, in the case of geothermal or hydro, the price is actually going up. Any ideas why that might be?
Environmental regulations, maybe taxing.
Could be, could be. Another possibility could be the higher cost, for instance, let's say, of raw materials such as cement or steel, or it could be even that the best sites were developed earlier, and now companies are moving into less advantageous sites that might have a higher price, but are still at a very low level in comparison with other technologies. You can see that the fossil fuel cost range is between $5 and about $17 here. So in order to compete with fossil fuels, renewable energy technologies should fall within this range. Any questions on this? No. If we now focus on just the levelized cost of electricity and auction prices for CSP technologies, from 2010 until 2022, we can see that there is quite a rapid decline. And recently, there were very low bids for CSP projects. So an example is the Dubai Electricity and Water Authority for a 700 megawatt plant. And it bidded for an auction price of $7.3 cents per kilowatt hour, which is quite low. And then there's the Port Augusta CSP project in Australia, which also bidded for a price of $6 per kilowatt hour. So you can see that overall the price is dropping and the technology is improving globally. If we look at parabolic troughs and solar towers, we can see what the outlook is for the next decade or so. So in this case, from an IRENA publication, they compare what the LCOE cost of 2017 was and what they projected it would be by 2025. So in the case of parabolic troughs, they estimate that a 37% decrease in LCOE price could be achieved, while for solar towers, this could be up to 43%. In the case of parabolic troughs, a lot of the price reduction could be attributed to temperature increases, which would also affect the necessity for a large storage system. So achieving higher temperatures would mean you need a lower storage system, so it reduces the cost of this storage. While a similar concept, switch over to salt as a heat transfer fluid would also contribute to a reduction in costs. Where for solar towers, the main area where cost could be reduced is the engineering, procurement, and contracting costs. And with more development of fields or projects, this cost is projected to decrease. Also, better heliostat placement algorithms, automation of operation and maintenance, etc., will account for the rest of the reduction for these technologies. So going back for the weighted average cost of capital and its effect on LCOE. First, the left-hand side of the slide refers to parabolic trough, and the right-hand side of the slide refers to solar tower. And each of these is divided into 2 years, 2015 and 2025. And making certain assumptions on the capital costs and the operation and maintenance costs, we can see what the LCOE would be for different levels of weighted average cost of capital. So you can see, for instance, in 2015, if the cost of capital is assumed to be 0 for parabolic troughs, then the LCOE, the levelized cost of electricity, is about at $8 per kilowatt hour. Well, if you increase up to 10% this cost of capital, it shoots up to almost $20 per kilowatt hour. So the cost of the financing costs, you can see that the financing costs affect massively the cost of electricity generation. But still, if we just focus on a cost of capital of 5% for each of the technologies, we can see a considerable improvement between 2015 and 2025 for each of these technologies. And in the case of parabolic troughs, the LCOE, the average LCOE, could drop down to $9 per kilowatt hour. And for towers, it could drop down to $8. And you can see that since there's improvements in the capital cost or reductions in the capital cost required for each of these technologies, the relative share of operation and maintenance costs basically grows. So the size of these orange bars grows over time. Okay, clear so far? So now looking into selected historical CSP data. So this figure shows CSP installed costs by project size, collector type, and amount of storage. So the crosses are linear Fresnel, bubbles are parabolic trough, and squares are solar towers. And again, the size of the dot is relative to the size of the power plant. You can see that the different color codes refer to the amount of storage that is installed for each of these projects. And you can see earlier in time, most of the projects installed were parabolic troughs, but now we can see that there are some solar towers and linear Fresnel being installed in more recent years. You can see in general that the trend is really going down in terms of investment costs. In terms of capacity factor, You can see that the capacity factor is improving with time. So basically, how much electricity is generated by each specific project. And again, you have the same characterization by size, collector type, and amount of storage. And these combined aspects, basically the investment cost and the capacity factor, have an equivalent effect on the LCOE cost of the CSP plants. And you can see that in general, the trend again is slow and it's going down for the cost of electricity from CSP. The levelized cost of electricity from CSP during 2013 and 14 is basically about 20% lower as compared to 2009 to 2012. And this coincided with a shift of geographical location. So the earlier projects were in Spain, and then projects started being developed in areas where higher direct normal irradiance was available. So higher capacity factor, higher output, so decrease in the LCOE. But these aspects that I showed don't really necessarily capture the entire outlook of CSP technologies. So maturity is an aspect. So as more projects are developed, the technology will improve. Wind and PV have a much larger installed base and have managed to reach lower costs much earlier. To give you context, in 2016, capacity additions on a global scale amounted to about 51 gigawatts for wind, 71 gigawatts for PV, but only 1 gigawatt for CSP. So as this number grows, we expect that the technology will improve and costs will reduce. The operational value of CSP is another aspect that should be taken into account. So CSP managed to avoid generation costs of baseload generation, fossil fuel generation, and provides ancillary services to the grid, while it can also avoid the cost of building new conventional generation. So it's a good substitute for that. Also, instead of looking at CSP as a competitor to other renewable energy technologies, it could be looked at as an enabler. So, especially with the availability of storage, CSP can coexist and it is not antagonistic to other intermittent renewable energy technologies. So, the existence of storage allows CSP to modify its output accordingly and match changes in supply and generation for the system in which it's developed. And finally, to close the session, I want to leave you with the goals that are set by different initiatives globally. So the Sunshot Initiative is a US effort that aims at bringing the LCOE cost of CSP down to 6 euro cents per kilowatt hour. As we saw, the project in Australia actually managed to reach that level. Then ASTRI, the Australian Solar Thermal Research Initiative, aims at bringing the LCOE of CSP down to 9 to 12 Australian dollar cents per kilowatt hour. In terms of US dollar cents, 9 is about 6.5 dollar cents. So it's relatively comparable. Target? Well, the EU has a target of reaching 10 euro cents per kilowatt hour. We need to take into account that in the EU, the direct normal irradiance is not as high as in other areas of the world. And with that, I would like to thank you and open for questions. Okay, it's all right. Yes.
Can we go back to that slide where you had the IRR going and
There are multiple IRR.
yeah,
yes.
because it goes against common sense that the discount rate, higher discount rate would be not good. So I want to see how realistic your example was.
Yes. Let me go back. Here.
Yeah, that one.
Yeah. So basically, these are the discount rates.
But actually go to the previous where you actually gave the, yes, here. So you had the investment cost was 235,000. So this is what I wanted to see, because then you said, it almost means that your equipment breaks down completely, and the second year you have to.
Yeah, there's another cost again. Yeah.
So it doesn't sound like a very realistic thing.
No, but it's just an example, a very simple example to show that if you have a mix of positive and negative cash flows, then you have a more complicated situation to play with. So it might not be a realistic example, but it's just to illustrate.
I'm trying to think, would there be any realistic situation where you would have, it's only like a total equipment breakdown, which is something that you can't anticipate.
Yeah, no, only in case of an accident. So to give you a good example from the Cyprus case, I don't know if you heard, in 2011 there was an explosion near the biggest power plant, and it was the newest power plant. And some of the units had just been installed. But then that's an accident, so it almost wiped out the power plant. But yes, I understand that. Yeah, this might not be a realistic example, but it's just to illustrate what could happen in case you have high equipment repair requirements for your particular.
And even it looks a little bit unrealistic that you would, in 1 year, you would generate double your, more than double your investment. So that would be an extremely good payback period.
Yes.
Doesn't have to be 1 year, it could be 10 years.
Yeah, you could assume that this is a decade, and
decade.
0 and 1 is a decade here, another decade there, for instance.
Yeah, okay, then it's more realistic.
Any other questions?